Hey everyone, in this video I'm going to explain to you the statement of the mean value theorem and also the intuition of what it means, what it means geometrically. So to get us started, let's imagine that we've got a function y equals f of x. I'll schematically draw such a function. Let's make it nice and simple so we can clearly explain the ideas. And so you've got your y equals f of x, and this is going to be defined on a closed interval. That's an interval that includes the endpoints from x equals a to x equals b, something like that. And the formal assumptions for the mean value theorem are going to ask that this function f is continuous on the closed interval and going to be differentiable at every point in the open interval, at every x value bigger than a, every x value less than b. So let's just keep on going with that understanding. And what you do is you say, well, I know how to make the secant line from a, f of a, to b, f of b, and I'll draw that secant line here. Here's a, f of a, here's b, f of b, and you just connect the dots to get that line. And this secant line has a formula. You might call it like L for line, and it's slope times the x value plus the y-intercept, whatever it is. Let's call that number e. You might say mx plus b, but we already used b for the right-hand endpoint. We'll use something else. And since it's a secant line, we know from earlier on that its slope, m, is just given by the formula f of b minus f of a divided by b minus a. And you could also interpret this in a physical context as the average rate of change, or if f was your position function, then this is your average velocity on the interval from a to b. For a general function, it's the slope of the secant line, as we've indicated there. And what the mean value theorem says is that in this setup, there must exist a point that's strictly bigger than a, strictly less than b. You call it c. It's somewhere around here. And this point has the following property. It has the property that if you actually take the derivative of f at the point c, then that's going to be equal to the slope of the secant line. It's going to be equal to f of b minus f of a, all divided by b minus a. And sometimes you'll see it written differently. Sometimes you'll see f of b minus f of a equals f prime of c times b minus a. So the mean value theorem, it's an existence theorem. It asserts the existence of a point c bigger than a, less than b, such that the instantaneous rate of change is actually equal to the average rate of change. Let me show you how to interpret this geometrically. So if you take that secant line there with slope m, you can imagine lifting it up or bringing it down. The slope doesn't change. And if you can lift it up, and if there's a time when that secant line actually becomes a tangent line for some point, then you've found that value c. So walk with me here. Imagine lifting this up and lifting this up, and where do you think it's going to stop and become the tangent line? I think it kind of stops right around here, and I didn't draw it quite so straight, but that's all right. You're lifting it up, kind of when you get that point, your tangent, and if you walk downstairs, you see that's where I marked that point C, because I knew in advance I was going to do this. But so that's telling you that this secant line, if you move it around, there's going to be some point C when it actually becomes the tangent line. In other words, there's going to be a point C where that derivative is actually equal to the slope. We really love this theorem in mathematics because it provides a link between the function itself and its derivative that's actually very important. In terms of immediate applications, there's one right now that I can give you. So say you're driving along the highway And if you're near to me, maybe that's the Mass Pike. Okay, and so say that the Department of Transportation set up 2 cameras on the highway. And the first camera, they take a position of you and they know your position. And then at the second camera, and they set up the second camera, it could be 60 miles away. They set up the second camera and then take a picture of you. And what they do is they start a timer after the first one and then take a picture. They know it's 60 miles away. They know how much time went by. So say that it only took you 1/2 of an hour to drive from here to here, that length, 60 miles, and you could have stopped along the way. You could have gone back and then gone forward some more or whatever, but whatever, the camera knows that you took 1/2 hour to go from here to here, and that distance was 60 miles. So if you imagine f as a function of t, being your position function, being your distance to that point right there, then what mean value theorem says is that when you look at the derivative of position, that's your velocity, there must be a point c, a point in time between that 1/2 hour that elapsed, with the following property, that your position at the end, your 60-mile difference, minus your position at the beginning, your 0-mile distance, divided by the difference in time, which is 1/2 hour, had to be equal to f prime of c, or your speed. Your speed at some time had to be 60 divided by 1/2. That's 120 miles per hour. Oops. So without having a fancy radar device, just 2 cameras at fixed distance apart and a clock, the Department of Transportation can just mail you a speeding ticket to your home using the power of calculus. Another situation where you might use this is where you've got a bridge or a tunnel and you really want to make sure people are going the right speed through that tunnel, but you can't set up the radar inside. Then you can see situations like this. We just have to measure the time that it took you to get across. We can use mathematics to make an assertion about your speed. So that might not be the most fun application, but it's one of the classic recognizable applications of the mean value theorem.